let me give a brief introduction of Professor Mitra, right? So Subhashish Mitra is a professor of electrical engineering and computer science at Stanford University. He directs the Stanford Robust Systems Group, leads the computing focus area of the Stanford System X Alliance, and is a member of the Wu-Tsai Neuroscience Institute. He also holds the Carnot Chair of Excellence in NanoSystems at CEA Lati in France. So he has done a lot of exciting research works. Okay, so I cannot enumerate all of them, right? But let me highlight several major ones. Okay, so with his students and collaborators, he demonstrated the first carbon nanotube computer. They also demonstrated the first 3D nanosystem with computer immersed in data storage, right? So this received a wide recognition, such as cover of Nature research highlight to the US Congress by the NSF, and highlight as important scientific breakthrough by global news organizations. So Professor Mitra's honors include the Newton Technical Impact Award in EDA, the Semiconductor Research Corporation's Technical Excellence Award, the Intel Achievement Award, which is Intel's highest honor, and the US Presidential Early Career Award. And he has published many award-winning papers, and so has been a key person in various services and societies, okay? And so he has been honored by Stanford undergrads and being the important person to them. And he's an ASM fellow and the IEEE fellow. Okay, all right, please go ahead, take it away.
Hey, thank you very much, Deming. And thank you, Deming and Celine and Mandy and all the organizers for inviting me to give this presentation. You know, it's really an honor to do it. Okay, so today I will talk about 21st century nanosystems for abundant data computing. Before I start this talk, I would like to thank my students, the sponsors, and my collaborators. They did all the hard work. Now I'm here to present their work. And so, you know, I really wanted to thank them first. To start this presentation, you know, let me point you to this study by the US National Academies. This is sort of an old study now because this was published in 2011 and today it's 10 years later, this is 2021. But this is actually a very relevant study. So I would highly encourage you to read this study if you have not. This is called The Future of Computing Performance, Game Over or Next Level. So what is the future of computing performance? Well, when we talk about computing performance, first let's define performance. In this presentation, I will define performance as energy times execution time. Why? Because there are many ways to improve energy at the cost of execution time. For example, to reduce voltage. There are ways to improve execution time at the cost of energy, for example, by increasing voltage. But there are very few ways of improving energy and execution time simultaneously. So that's why the focus is on energy times execution time as a notion of performance. So why did that National Academy study talked about the future of computing performance? That's because if we look at the most exciting applications today, and I call those abundant data applications, because they operate on a lot of data, and AI machine learning being an example of abundant data applications. Other examples would include, for example, graph analytics and so on and so forth. There are some major challenges that the world is facing. The first major challenge is what is called the memory wall. If you look at the pie chart over here, you see that I haven't said whether this represents what, you know, whether it represents energy, execution time, or what. Because in some sense, it does not matter. The point I'm trying to make over here is that a large proportion of resources let's say either energy or execution time, is spent trying to access the memory. And this is irrespective of the fact that whether we are talking about von Neumann architectures, for example, processors, or we are talking about, for example, hardwired hardware accelerators that are non-von Neumann, and they also face this so-called memory wall. The other elephant in the room is the miniaturization wall. Depending on who you talk to today, we are at a 5 nanometer technology node or a 3 nanometer technology node. And the question is how far we are going to go beyond that. Maybe we will go up to 0.5 nanometer technology node. That's what I'm showing by these Russian dolls. And those font sizes actually, show that progression of, 0.7 every generation. So bottom line, by the end of this decade, we are going to hit the miniaturization wall, which means that it would be extremely difficult to keep making things smaller and smaller. And oh, by the way, in addition to that, there are many other walls. For example, we have been dealing with the power wall for a while now, and then we have the cooling wall and resilience wall and so on and so forth. So given all these walls, how do we overcome these walls and achieve, for example, major performance benefits? Before we even do that, we need to look at what does it mean to make progress in the semiconductor technology. Today, we talk about technology node being a notion of progress. But moving forward, clearly, when we hit that miniaturization wall, we are probably not going to make the technology node smaller anymore. So I would encourage you to read this paper that was written by a bunch of us, led by my collaborator, Professor Philip Wang, which argues for a different metric for semiconductor technology. And specifically, this paper argues for an LNC metric, where we look at logic density, memory density, and very importantly, connection density as a metric to gauge progress in semiconductor technology than the technology node that we have been using for a very long time. So to improve computing performance, again, performance is energy times execution time, we cannot get that performance improvement, especially when we are looking at 1000x improvement in performance. We cannot get that just by technologies or just by design techniques. We have to use a combination of technologies and design approaches to achieve 1000 times improvement in computing performance. And that gives a notion of what I call nanosystems. So what are nanosystems? You start with nanotechnologies, and this could be new kinds of devices, new fabrication approaches, new kinds of sensors, and so on. Now, when you talk about nanotechnologies, on one end of the spectrum, you're talking about something very small. I'm going to talk about stuff at the level of 1 nanometer. And on the other end of the spectrum, you're talking about lots of those. So then you have to overcome challenges with imperfections, variations, large-scale fabrication, and so on. And when you are successful, it's extremely important that we enable some new architectures that are extremely difficult or impossible with existing technologies. We cannot take an existing architecture and just replace existing technologies with new technologies. If we do that, then the fundamental bottlenecks of those existing architectures will not be overcome. So we need new nanotechnologies to enable new architectures that are not possible with existing technologies. And those new architectures will hopefully enable new applications. In our case, abundant data applications such as AI machine learning. So if we look at computing today, this is how it looks. You get a computing chip, you got a memory chip, which is very far from the computing chip. Remember, this is irrespective of the fact that whether you have a von Neumann architecture or a non-von Neumann architecture. And then you spend all your time and energy going back and forth between the compute chip and the memory chip. Instead, tomorrow, for our next nanosystems, what we got is something like the following. You got multiple layers of efficient logic. You got multiple layers of dense and efficient memory that are interleaved with each other. You could have a layer of increased functionality, for example, new kinds of sensors. But if I wanted you to carry one most important message from this presentation, that is this ultra dense and 3D vertical connectivity between these various layers. So now this one overcomes many walls that we were talking about earlier. First of all, we have efficient logic and dense and efficient memory that overcomes the power wall. It overcomes the memory wall because now memory and logic are very densely interleaved with each other. And it overcomes the miniaturization wall because you go into the third dimension. But remember, the most important point is ultra dense and fine-grained three-dimensional integration. And this is something that is impossible with business as usual. But when you create something like this, you enable what I call computation immersed in memory. Now, next is a concept. And the question is, how do you implement next? There could be many ways of implementing the next concept. And in our presentation, I will focus on certain ways of implementing next. But one really important point is, when you have the next dense 3D chips, it's not that you're going to have an infinite number of layers of next 3D, which means that we also have to think about what I call this notion of a 3D mosaic, which is if you have multiple of these next dense 3D chips, they are sitting on some kind of an interposer or some kind of a packaging with very efficient connectivity between the next dense 3D chips to enable what I call a 3D mosaic. We'll come back to all these points later in this presentation. So in the first part of the presentation, let's focus on how we implement next. As I was talking about earlier, next is a concept. There might be multiple ways of implementing it, and let's focus on certain implementations. You can learn a lot about this next concept from our papers that we have published earlier, especially the most recent being the Proceedings of the IEEE in 2019, that has very detailed discussions and quantitative benchmarking of next. So as I was saying, for our next implementation, for logic, we are focusing on mostly one-dimensional carbon nanotube transistors, and we also look at two-dimensional FETs. For memories, we look at magnetic RAM and three-dimensional resistive RAM because they have complementary properties with respect to energy, with respect to retention, with respect to endurance and density. You can think of other RAM approaches, for example, gain cell-based approaches and obviously SRAM as well. But there are three really important points I want to make over here. The first point I want to remind you about this ultra-dense vertical 3D connectivity. This is achieved using ultra-dense fine-grained vertical vias and not through silicon vias. That's the first point. The second point is this entire next structure is fully compatible with silicon technologies that can be built in silicon fabrication facilities. And number three, when you think about 3D, the first thing that comes to your mind is, oh my goodness, how are we going to deal with thermal? Now, when you have logic on the upper layers of a 3D stack, that does not necessarily mean that that logic is running at whatever gigahertz to do compute. That logic can mostly be used for memory accesses. So in the first generation of our next architecture, the logic that's on the upper layers are for memory accesses only, and it's cold. And as a result, you do not have to worry about thermal. But when we really reach a situation where two-dimensional miniaturization has really stopped, then you have to think about running heavy-duty compute on the upper layers, and that's when thermal becomes extremely important. And this next concept is the foundation for a major program by DARPA. This is the 3D SoC program, a joint collaboration between MIT, Stanford, Skywater Technology Foundry. This is a US silicon foundry, and NanoIntegris, a carbon nanotube provider. So I will very quickly touch upon the various aspects of our next implementation. First, carbon nanotube transistors. Carbon nanotubes are nanocylinders of graphene with fantastic electrical properties. When you grow carbon nanotubes on a substrate or transfer carbon nanotubes from one substrate to another substrate and create source, drain, and gate contacts, you get a carbon nanotube transistor. And as our prior work in collaboration with IMEC has shown, that carbon nanotube transistors, when you replace silicon transistors with carbon nanotube transistors in digital systems, you get very large benefits in energy delay product right off the bat. In the past, for a very long time, manufacturing carbon nanotube circuits used to be a big challenge, but that challenge has been overcome using an approach called imperfection immune paradigm. And as a result, today we can build very large-scale carbon nanotube designs, the latest being the work by MIT and Analog Devices on a full RISC-V carbon nanotube processor. The other aspect of carbon nanotubes is that it's not only just the work that we have been doing at Stanford, but all over the world, there have been very significant advances in carbon nanotubes, both with respect to scalability, with respect to complexity, and with respect to performance. One of the latest being the work by TSMC that was published in IEDM, last December on, very interesting gate dielectrics for carbon nanotube transistors. Beyond logic, a very important aspect of next is, on-chip memory, large amount of on-chip memory, and that is enabled by what we call is resistive RAM. I will get back to these aspects of resistive RAM later in this presentation, but this is key to achieve what I call 10-year edge AI. But the third important aspect, perhaps the most important aspect of next, is the dense 3D integration. Today, the world uses what I call very sparse 3D using through silicon vias. These are these big fat pillars that are connecting busy cities, memory and compute, for example. What we are focusing on in next is dense monolithic 3D that's enabled by highly dense back-end of line metal vias that you already have inside your integrated circuits. These are used to connect the vertical layers of metal interconnects. And the question is, why don't we put transistors and memory cells on all those vertical layers in an integrated circuit that would give me perhaps the densest vertical connectivity known to humankind? Now, this is something that's very difficult with existing silicon technologies. That's because it takes you 1,000 degrees C to build silicon transistors. And when you build silicon transistors on the top, what would happen is, at a very high temperature, everything underneath that you built would be severely damaged. And here comes something that's unique about these component technologies. For example, the carbon nanotube transistors or the resistive RAM that I talked about earlier. You can build those technologies at a very low temperature of less than 400 degrees C. So not only do you get the technology level benefits of these component technologies, the carbon nanotubes and the resistive RAM, you enable a new architecture, which is this ultra-dense and fine-grained monolithic 3D integration that is extremely difficult, if not impossible, with existing silicon technologies. So you get not only the device level benefits, but also you get the architectural level benefits of a dense monolithic 3D. And over the past several years, starting from the Nature paper, the 3D NanoSystem back in 2017, year after year, our group has demonstrated these 3D nanosystems in the lab, 3D nanosystem, the Nature paper, then hyperdimensional computing, then non-volatile IoT, illusion, something that I will talk about later in this presentation, and the latest being the edge AI training and inference that was presented at VLSI Circuits in June this year. But this also has enabled the proverbial lab to fab. I'm very proud to tell you that all these component technologies we are talking about, the carbon nanotube transistors, the resistive RAM, the monolithic 3D, it's not only that we can build those things in a Stanford lab. As part of the DARPA 3D SoC program, in collaboration with MIT and Skywater Technology Foundry, these things are working in an actual commercial silicon foundry. So this is not just some hokey pokey lab thing. This works in a commercial silicon foundry using commercial silicon fabrication tools. Another very important aspect of NeXT is, although our specific NeXT implementation, for example, focuses on carbon nanotube transistors, resistive RAM, and monolithic dense 3D, you might have some other ideas of heterogeneous nanotechnologies. So that's where the NeXT simulation framework becomes extremely important, where on one end of the spectrum, you take heterogeneous nanotechnologies. On the other end of the spectrum, you take abundant data applications, for example, using PyTorch or TensorFlow or GraphLab. And then you actually perform a system level analysis by exploring a wide variety of architectures. And just architectural level exploration is not good enough. You have to have a physical design of all this dense 3D so that actually you know that the architectures are actually implementable. And then you can extract R's and C's and so on. And you can calculate energy and execution time, thermal and lifetime, and so on. And using the NeXT simulation framework, we can show that for a wide variety of abundant data applications, conventional machine learning, deep learning, graph analytics, and so on, over and over, you achieve very large benefits at the scale of 1000x improvement in energy times execution time using existing software, which means that if you improve the software, you would get even higher benefits. But using existing software, you get these very large benefits using this NeXT approach. And this NeXT simulation framework is then used not only to quantify the massive NeXT benefits, but also to perform what is fashionably called co-design today, which is to co-explore the interplay between technology, architecture, and applications. Here is one example. Let's take this example of an LSTM. And we are trying to understand what is the impact of the vertical 3D connectivity on the energy delay product. You could use, for example, a 5-micron pitch vias. That would be even slightly better than the 10-micron through silicon vias that the world uses today. As you can see that the benefits are not much. Actually, most of the benefits come from carbon nanotubes in that case, and then you see that you have small benefits, non-negligible, but small. But when you decrease your via pitch, which means when you increase your 3D via density that is achievable by monolithic 3D integration, you see the massive improvement in energy delay product that you get. So this kind of a co-exploration of technology, architecture, and applications is going to be crucial moving forward. So this creates many nanosystems opportunities. And I will focus on the first one, which is how do you co-design between device technologies, circuits, architectures, and algorithms. This algorithms piece is also going to be something extremely important that I will emphasize when I go over the rest of my talk. I won't have time to talk about dense compute plus thermal, which is going to be important when that two-dimensional miniaturization stops, when you put heavy-duty compute on the upper layers of NeXT. And I won't have time to talk about new software optimizations as well. But let's focus on the first one. And I will show you 3 demonstrations. First, the non-volatile IoT. The second is the first demonstration of non-volatile edge AI that performs both training and inference at the edge. And the third one is a notion of what is called illusion scale-up. So I'm very thankful that in collaboration with CELAT, we were able to demonstrate, this was in ISSCC 2019, a non-volatile IoT chip where on top of commercial silicon CMOS, we were able to integrate CELAT's resistive RAM. And as a result, we were able to perform an apples-to-apples comparison of our IoT chip with respect to an industry chip with embedded flash. And we were able to show apples to apples in hardware, 11 to 28x lower system level energy during normal operation. And I will also touch upon multiple bits per cell. What is even more interesting is when you turn this off, to bring it back, the resistive RAM-based IoT chip was enabled a 5,000x quicker shutdown compared to the flash chip, which enables fine-grained temporal power gating. And this is, remember, all in hardware. You can demonstrate a 10x improvement in battery life using a resistive RAM-based IoT. So in real life, in actual hardware, using a new technology, you get a 10x benefit, which is very significant as you can get. When you think of these non-volatile memory technologies, you also have to think about their reliability, especially with respect to endurance. And again, using a new endurance technique called Endurer, we were able to demonstrate 10-year lifetime running inference continuously at the edge. You can ask me a question that how did we do a 10-year lifetime measurement? I can answer that if you have that question later. And very excitingly, this also allowed us to demonstrate for the first time multiple bits per cell resistive RAM system. Before this work, people were mostly demonstrating at a single cell level that if you had one resistive RAM cell, you can get some benefits. Like you could get maybe two bits per cell, 3 bits per cell, and so on. But what matters is at a full array level, how do you get multiple bits per cell? Because to do that, you have to think about clever algorithms to read and write resistive RAM. And not only that, you also have to think about variability. And for example, when you're thinking about neural nets, how do you optimally encode the weights of a neural net that take advantage of this on-chip resistive RAM? Because now you could fit in a bigger model, and how do you actually achieve more accurate inference as a result? I would strongly encourage you to read our ISSCC 2019 paper for that. But not only that, since then, we have been able to demonstrate very significant improvements in density of resistive RAM. So typically when people think about a resistive RAM, they think about one transistor, one resistive RAM cell. And your footprint of your resistive RAM is dominated by your transistor. So in this EDL paper, the electronic device layers paper, last March, we were able to demonstrate what are called 1T8R resistive RAM, which means for one select transistor, you have 8 resistive RAM cells. And not only that, in each of those 8 resistive RAM cells, you store 4 bits per cell. So you get massive improvements in density by using this 1T8R 4 bits per cell resistive RAM. At VLSI Circuits, in June last month, we were able to demonstrate the first AGI non-volatile chip using on foundry resistive RAM that can perform both inference and training. As you know very well, there are lots of chips that perform AI inference. And this chip that we have, this is called Chimera. It had 2 megabytes of foundry resistive RAM. And when we build chips today, I tell my students, we cannot have any off-chip memory. No off-chip memory, because we do not want any memory wall. So this chip had 2 megabytes of on-chip resistive RAM, no off-chip memory. And on this chip, we are able to show a new incremental training algorithm, which is aware of the resistive RAM. If you try to perform stochastic gradient descent based training at the edge, you will perform that because of limited endurance, because of high write energy of these non-volatile memories, it would be a disaster. But here's an example of co-design where we had to create a new algorithm that was enabled, that is aware of the underlying characteristics of the resistive RAM. And as a result, we can show 10 years of incremental training at the edge at 20 samples coming in per minute. And this allows 340x lower energy delay product compared to stochastic gradient descent. Because we just have on-chip resistive RAM and we do not have any off-chip memory accesses, we could now optimize our inference hardware as well for resistive RAM, and we could achieve, as you can see, very good tops and tops per watt, And we could even significantly reduce the amount of on-chip resistive RAM on-chip SRAM that you would need. But this chip only has 2 megabytes of on-chip resistive RAM, and you might be rolling your eyes saying 2 megabytes is not enough for the workloads that we care about. For example, if you were looking at ResNet 18, that would require 12 megabytes of resistive RAM, but we only have 2 megabytes. How do we enable 12 megabytes model running on a 2 megabyte of resistive RAM? That gives a concept of what we call new illusion scale-up. That will be the last part of my presentation. So now I will focus on the last part, which is illusion scale-up, and then I will wrap up my talk. So what did we talk about? What is the dream chip for AI, given all that we said? Well, the dream chip of AI would be that all compute and all memory should be on chip, quickly accessible at low energy. Now, this dream chip is infeasible for the following reason, but it doesn't really matter how we build the dream chip. We could do all our next 3D, but the applications are growing much faster than technology. So we will never be able to fit any neural network, for example, on our existing chips because the neural networks keep growing. So dream chip is almost infeasible. And as a result, what the world does today is that you have the compute chip and a separate memory chip. And we already talked about the memory wall going back and forth between the compute chip and the memory chip. And here comes a new idea, which we call illusion. Here, what we are doing is that, remember that we want the dream chip that has amount of memory which is n times m, but our technology only allows us to provide m amount of memory per chip. So what do? We actually take n of these chips and we create an illusion system which has an interchip network, and the overall memory in the system is still n times m. Now, there are certain aspects of this. Unlike a conventional system where some chips can compute and some chips can store, now you have every chip can compute and every chip can store, which means that to perform some computation, you do not have to bring the data from where the data resides to the chip where you want to compute. Instead, you can send the compute to the place where the data resides. And as a result, as long as you compute on a lot of data and produce small results, you will get massive benefits. So the whole notion of illusion relies on the following fact. A, you have enough on-chip memory. B, you are able to turn these chips on and off very quickly so that you don't waste any leakage energy. And once you have this 1 and 2, then you perform a special mapping, which we call illusion mapping, on this multi-chip system so that the interchip network is very sparsely used. And that creates an illusion of the dream chip. And this illusion is different from traditional multi-chip parallelization. Multi-chip parallelization is known since the 1960s, for example, ILIAC 4 from the University of Illinois, versus the way that this dream chip is done, this illusion is done, it creates an illusion of dream that multi-chip parallelization cannot do. So as a result, we were able to show in multiple hardware, 8-chip illusion, 6-chip illusion, you can see that the overall energy of the illusion system is within 4% of the energy of the dream chip that you could not build. And the overall execution time of the illusion system is within 3% of the dream chip that you could not build, which means that you can mathematically prove that you can actually create an illusion system that's within 5% of the energy and the execution time. And this is ideal for AI workloads such as inference and training. I'll just give you, and I won't have the time to go through the details of the illusion, and I will wrap up. But I will just give you a little sense for how this illusion mapping works, because this illusion mapping is very important. Let's take ResNet 18. Here is an illusion mapping. ResNet 18 is like a 12 megabyte model. And you can see that the number of messages that are going back and forth between the various chips is only 265 kilobytes, which is extremely small compared to a 12 megabytes model. If you had a chip storing 2 megabytes, for example, with a conventional approach, you will have 10 megabytes stored off chip, and that would be a message size of 10 megabytes. Versus Illusion gives you only a message size of 265 kilobytes. And there are multiple Illusion mappings possible to trade off between energy and latency, and still you can see that you have less than 1 megabyte of messages going back and forth between the various chips. Versus if you take a traditional multi-chip parallelization, for example, the work called Simba from NVIDIA, you see that for a 12 megabyte model, the amount of messages that you need is 10.5 megabytes. So that's almost similar to just having an off-chip memory. So as a result, at a full system level, compared to traditional multi-chip parallelization, you get a 5x improvement in EDP using this concept of illusion. And not only is this useful for single inferences, but even if you use multiple inferences, the same story, you have 1.8 gigabytes model, and you see that you are only using close to 1 megabyte of sparse messages going between the various chips. And that is the key to achieving illusion. So this creates a great opportunity, which is the following. For the past 60 years, we followed, this is a slide borrowed from Professor Philip Wong, I call the miniaturization tunnel. Miniaturization, miniaturization, and more miniaturization. And we are reaching the miniaturization wall. But moving forward, we actually have a football field to play with. We have more on-chip integration using next dense 3D, for example, on the y-axis, but also better inter-chip integration through better packaging. But those two alone are not enough. Those two, when combined with illusion, creates the illusion of the dream chip, and that is the key of new kind of a scale-up moving forward. So for example, take an example here, which is an LSTM language model. As I was saying, the y-axis says more and more integration. The x-axis talks about better inter-chip integration given by the network performance between the chips. What is the world doing today? People that work on chiplets that are pushing only this inter-chip integration axis. If you just do next 3D, you are pushing the y-axis, which is more on-chip integration. But when you do illusion, you combine the two, and you can see the following properties. First of all, if you look at these ISO lines, on this line, your illusion EDP of the illusion system, you are within 10% of the dream chip, which is a massive improvement. But what it says is that you have a major trade-offs between how much on-chip integration you need versus how much better your inter-chip integration has to be. But even more importantly, when you scale, you go from one illusion line to another illusion line. If you do not improve your on-chip integration, then you need a massive improvement in your inter-chip network, which is difficult to do. If you do not improve your inter-chip integration, then you need a large improvement in your on-chip integration. That means a lot of 3D. But when you combine the improvement in on-chip integration and inter-chip integration, then diagonally you can go very easily from one illusion line to the next better illusion line. And that is the key to future scaling when the miniaturization wall stops. I just want to take 1 second to make a word. We mostly focused about next 3D and illusion and so on. When we build these complex systems, we cannot forget that it's not just about the energy delay product and performance. It's equally about robustness. How do we validate such systems? How do we test such systems? And how do we actually improve the reliability of such systems? And if you read recent papers from Facebook and Google, you will see the importance of this. Especially Google had a paper in HotOS talking about codes that don't count. I would strongly encourage you to read those papers to make the point that how do we revolutionize system validation, test, and resilience? These are going to be the key when we actually build these extremely complex systems using this next 3D mosaic and illusion. So to conclude this presentation, I want to make a few points. First of all, NanoSystems can be achieved today. I gave you commercial examples from commercial foundries, CNFET's resistive RAM and monolithic 3D. So the question that I posed right in the beginning, the future of computing performance, it's game on with Next, 3D Mosaic, and co-design spanning device technologies, circuits, architecture, and algorithms. And the new Illusion scale-up is the key to very large benefits for a wide range of applications. Thank you very much for your attention. I think I went a little over, and I'll be glad to take questions.
Right, Subhasish, thank you very much for this excellent and inspiring keynote. Yeah, so I think your timing is good. So we still have time for questions and answers. And there are some questions posted in the chat. Let me read them. So the first one is from Zheng Man. For the illusion system evaluation, what happens if you have a large network model that goes way beyond of the total on-chip size?
Thank you very much for asking that question. So, I couldn't get a better question than this, and I didn't have the time to talk about it. So what we have demonstrated is the following, first of all, right? When you have an 8-chip illusion or a 6-chip illusion, and I'm very careful in how I say it, so please do not misquote me on this. That is equivalent to 3 generations of Moore's law. Because remember, the dream chip is 8x bigger than individual chip in the 8-chip illusion, right? So you already got 3 generations of Moore's law, kind of, you get 3 illusion basically. But that's for an 8-chip illusion. And that's for a board that we built, that my students built, right? Why? Because an interposer-based integration is very difficult to do at a university today. And this actually creates opportunities for design automation and new ways of doing technologies. So even for a board, a conventional board that has 60 picojoules per bit to drive the messages between multiple chips, we actually achieve that 5% illusion. Which means that when you actually have a better interposer, you can actually achieve a lot more chips. And so if you look at our Nature Electronics paper that came out in January this year, there we simulated, you could actually have a 64-chip illusion, which is 6 generations of Moore's law, okay? So that's exactly my point that I was making on my last slide, that it's not just about on-chip integration, it's about how you improve your inter-chip integration. And when you improve your inter-chip integration, you get a new cadence. It's almost like, just like what we say today that, you get, 2x, more transistors, every whatever number of years. Now you say, well, every whatever number of years, you get so much more on-chip integration. And oh, by the way, your inter-chip integration also has to improve by so much. And once you keep this cadence, you actually enable bigger and bigger illusion systems. I hope that kind of answers your question. There are more questions that I would take, but if it does not, please ask me more questions.
Right, so there's a break right after this, right? So Subhasish, if you can stay a little bit longer, right? So I'm sure more questions. So the next one is from Jason Anderson. For RAM, could you comment on whether it's ready for widespread commercial deployment?
Actually, it is ready, and foundries are providing that. Multiple foundries, so yes, it is ready. And that was the whole point of our VLSI circuits paper, Jason. I would very strongly encourage you to read the paper. We did not even go and change the macro that the foundry provided us. Why? Because exactly the reason that you just talked about. Because, I can fiddle with the macro and do interesting things, but that would not serve anybody's purpose. The whole point was to show, A, that taking a foundry resistive RAM and foundry macro, you can go through the whole design methodology and you can actually build something. And not only that you can build something, like the foundry builds that, right? Not only you can build something, yet it actually gives you massive benefits, both in terms of inference and also new kinds of training for edge AI. So that was the whole point. Great question, happy to chat more.
Great. All right, so the next one is from Fan Chen. So the 10-year inference lifetime of Enduro is very impressive. So can you talk about how you achieve it? So what's the trade-off here?
Thank you very much. So I would not say that there is much of a trade-off. But obviously, think of the following, Fan, that if you have an application, my application, what it just did is that I have a whole bunch of finite state machines on my silicon. And what that finite state machine does is that it just keeps writing every cycle for 10 to the 12 cycles. Then, even God cannot save us, right? So of course, the application has to have some envelope of the number of writes. But once you have that envelope of number of writes, what we are doing under the hood is that we are doing some kind of a wear leveling. Now, wear leveling is not a new concept. Many people do wear leveling. The Flash people do wear leveling. But there are certain important aspects of Endurer which is very different from what Flash people would do, for example, for wear leveling. Number one, resistive RAM is accessible not as pages. Resistive RAM is accessible as your words. So you can actually do word level wear leveling, which is extremely difficult to do for Flash and stuff like that, number one. Number two, Endurer is a very simple technique. We do not need like 100 tables to store our, like indices and stuff like that. And so that we can do mapping and remapping, a very complex thing. You can do that for storage, but you cannot do that for kind of main memory. Instead, actually, Endurer relies on randomized algorithms to do this thing. So I would, encourage you to read the paper. And the third piece is the following, which is now you will ask me, but what if I have an application that does not fit your write envelope? I cannot use Endurer, right? And that's where this notion of co-design comes into play. If you take stochastic gradient descent-based training, it will be gone. But because we actually have a new training algorithm called LRT, or low rank training, now actually we can actually use that low rank training in conjunction with Endurer. And I showed you that, I can do incremental AGI training, and I can do 10 years. So this co-design is going to play a very important role. And that's the point I'm trying to make.
Great. Yeah, thank you. So last question before we close this session, right? This is from He Li, right? Thanks for the talk. Here's a high-level question. How would you feel that in the nanotech era, while the high density photonic electronic co-design by means of CMOS technology becomes a popular trend? So also, how about this photonic quantum computing?
Okay, I'm not going to say anything about photonic quantum computing because I'm an idiot about quantum computing, okay? But I do want to make 2 points, including one on quantum computing. So first of all, remember that I was talking about this illusion scale-up, right? Which is on one axis is more on-chip integration, but the other axis was better inter-chip network. And this is where at an interposer level, very efficient photonics could be extremely useful before you even think about on-chip photonics, right? That's kind of, this photonic electronic co-design. I agree with you, this is going to be extremely important moving forward. But one point I just want to make about quantum computing hardware, remember, a quantum computing hardware is not just going to exist on its own. It's not like, oh, if I build a quantum computer, all these things that we are doing is going to be relevant. Actually, it's going to be more relevant because when you have a quantum computing hardware, that has to be controlled by these electronic systems, and that's where some interesting breakthroughs would happen. Thank you very much. I'm happy to take more questions, or you can send me email, you can look me up, and I'm happy to take more questions.
Excellent. Yeah, thank you very much, Subhashish. Right. So actually, I'm going to post this Gather Town link in the chat. Okay, so if you have several moments, maybe you can visit the Gather Town. And in the area, right? I'm sure people can approach you and form a bubble and further discussions.
Thank you very much. I will do that. Thanks a lot.
Great, great.